Surprise, it's me. I wanted to make you guys a little video just to show you how I do these calculations. I think it is the easiest, most foolproof way. But these calculations are super important, normally contributing towards a E question. So it's vital that you guys know how to do it correctly every single time, no matter what they give you. So, hopefully you guys would have already gone through the slides. This equation is nothing new to you. You learned it last year, and we also used it in 2.1, so that's nice and familiar. But we've got this new equation, change in enthalpy equals heat energy, Q, divided by moles. Right, and so that's what we're going to be looking at now. This first question from the 2019 exam is a nice easy one to start off with. We are just looking at O2 in the equation, and we're trying to find the mass of oxygen required to produce 1,804.5 kilojoules of energy. I want you to quickly pause the video. That sounds super cringy, but pause the video. You're going to be doing that a little bit today, just so you give it a go before I go through the answer. But this one's starting off nice and simple, so go ahead, give it a go, and then press play when you're ready, and I'll go through the answer. All right, so cool. Right, nice and easy. We're trying to find the mass of oxygen required. Before we do that, we need to obviously find the moles. So moles of O2 based on my information from the equation and the reaction. So 1 mole of oxygen when it reacted produced 1203 kilojoules of energy. So moles equals Q divided by delta H. Now, it produced 1,804.5. Whenever we are releasing or producing energy, it means the system, so remember the system is the reaction, has lost this much energy, which means in terms of heat energy, I've lost it. So it's negative Q. So I'm going to make it negative 1804.5 divided by negative 1203. Okay, pop it in my calculator and I get 1804 divided by 1203, and I get 1.5 moles. Now, a great reminder whenever you're trying to find a mass of something, it only works in this direction, unfortunately. But if I forgot about this negative here and I didn't put it in, I would get a negative mole value. And remember, moles is just the number of particles, and I can't have a value that's less than 0 of number of particles. That it just doesn't make sense. It can't go negatives. All right, so that should be a really big indicator that you have forgotten it. Okay, so moles, just like mass, should always be positive. Alright, then it's just nice and simple. We go mass, O2, use that equation that we know and love, and we go 1.5 times 32, because obviously 16 times 2, and we get 48.0, because remember, 3 significant figures always, 48.0 grams. Okay, nice and easy. So that's the first equation. Okay, kind of like an achieved skill, I guess. Now, the second equation, we're trying to calculate the energy change. So we're trying to find Q, and we've got a mass of magnesium oxide, and then they've even given us the mass of magnesium oxide because they are molar mass, because they are feeling nice to us. Okay, so I'm trying to find Q, and I've got a mass of magnesium oxide. When I look at magnesium oxide in the equation, I see that it is 2 moles of magnesium oxide. So remember that delta RH is the enthalpy change for 1 mole of reaction. So that's what this little 1 mole is. It's per mole of the reaction, which means I've got 1 of this entire thing. But when I am working with my values, I am trying to work with 1 mole of the substance being magnesium oxide. And we see that there's 2 moles of magnesium oxide. Okay, I want it to be on a 1 mole scale for the substance. 1 mole of the substance. So I'm going to divide that by 2. But I also need to figure out if 2 moles of magnesium oxide produces 1200 kilojoules, then if I only have 1 mole of magnesium oxide, it's going to produce half of that. So my delta H for 1 mole of magnesium oxide is 1203 divided by 2, which is 601. Don't forget the negative. So negative 601 kilojoules per mole. And this is the value that I am going to be using in my equation, because I want everything to be in terms of 1 mole of the substance magnesium oxide. Another way of thinking about this is if you were cooking a recipe. Okay, most recipes serve like 4 people, and it required, let's say, 2 cups of milk. Okay, so 2 cups of milk is how much milk I'd need for my 4 servings of, I don't know, lasagna. Okay, but I am just wanting to make 1 serving of lasagna. So to find out how many cups of milk I'm going to need, I'm going to divide it by 4. Okay, so I'd only need half a cup if I was just making 1 meal. So it's all the same thing. We're just applying the ratio to the recipe. So I'm finding out 1 mole magnesium oxide produces 601.5 kilojoules of energy. So coming back to my question. So immediately what I can do is I can calculate the moles of magnesium oxide. And so moles is mass divided by molar mass. My mass is 100, molar mass is 40.3. 3, and I get 2.48 mole. Okay, so 2.48 mole. I then can calculate the amount of heat energy that is either going to be produced or absorbed. So Q is equal to delta H times by my moles. Delta H, I use that new value in terms of 1 mole of the substance, times it by how many moles I have in 100 grams. Remember to use your unrounded value. So I'm going to times by negative 601.5 in my calculator, and I get negative 1490, keep it to 3 sig fig, kilojoules. Now this means that 1490 kilojoules of energy was released. Okay, so you either just leave it as negative 1490, or you can write a sentence. So 100 grams of magnesium oxide produces or releases 1490 kilojoules of heat. Okay, that's another way of putting it. But you either do the negative sign or you say that produced. Okay, if you do both, you're kind of canceling those out. Alright, so that's just an example. This is kind of as tricky as it gets, just when you're dealing with a different ratio. Alright, so it's not just a 1 mole of something. We've got some more practices. So again, I'll get you to pause the video. Give this one a go. Okay, it's following the exact same thing that I did before. And when you're ready, replay the video and I'll go through the answer and you can check if you've done it correctly. Feel free to just skip ahead if you don't need the explanation. Just check if you've got the answer correctly. Or if you think you've got it nailed, you can just go back to the PowerPoint and look at the answers on those slides. Okay, right. So either pause the video or whatever you feel like. So this time we are looking at butane. So butane is this guy, and I've got my delta H immediately because if I read ahead, I'm trying to find the energy release when I've got this much butane. I know everything is in terms of butane, which means that I am going to divide this by 2, because remember you want it in terms of 1 mole of the substance. So if you do that straight away, it means that you will not forget to divide it by. Now, some people prefer to kind of divide or sort out the moles later on. The problem is, depending on the direction you're going, so whether you're calculating energy or whether you're calculating mass, you'd either have to times or divide. So this is the most straightforward way, most foolproof way, I should say, to get this correct. So 288 kilojoules per mole. And I'm actually going to go ahead and get rid of that. That's the value that I want to look at. Right, so we are trying to calculate Q. So the first thing that I need to figure out is the moles of butane, C4H10, which is equal to 450 grams divided by 58. So 450 divided by 58 is 7.76 moles. Okay, then we're finding Q again. So just like last time. Alright, so delta H, oops, almost did a really common mistake. Negative 2880 times 7.76. That is a really common mistake to do. Please do not make it. Negative 2880. That's minus 22,300 if we're doing it to 3 sig fig, which you should be always. Don't forget it is in kilojoules. Now, sometimes the question will say calculate the energy released. And obviously if we're saying that there's a negative 22,300 kilojoules released, that's kind of cancelling it out because I know that it's 22,300 kilojoules that was released. So again, just like we did up here, I am just going to write a sentence just for clarity. So 450 grams of butane releases 22,300 kilojoules of heat. There. No, none. Alright, one last one. Okay, practice 3. You can see that they love asking about the combustion of fuels. Right, this time in 2016 it was hexane. Okay, but this one's asking you about 2. Okay, so it's asking you about pentane combustion, hexane combustion, and then it's asking which will produce more heat. So have a read through the whole question, pause the video, and again, you can either skip to my answer or follow the working through, totally up to you. Alright, so I'm just going to do pentane in yellow. So pentane, we're looking at this one and this one. For both of the fuels, we're using 125 grams. And then if I'm looking at hexane, also using 125 grams. Now I've seen with hexane, there's that cheeky 2. I'm going to go ahead and make sure I'm talking about 1 mole of the substance. So before I even start any calculations, I know that I have sorted that. So -4.158 kilojoules per mole. Go ahead and highlight that value. Cool. Right, so it's normally nice and clear. It really helps with the marker if you just split it into 2. So I'm going to do pentane first. So we can get the moles first. C5H12. Really important to make sure you say what you're talking about to make it super clear for the marker what you're calculating where. So we've got 125 grams of the fuel. Molar mass is 72, which is 1.74 moles. Okay, and then Q equals delta H times N. Delta H, because it's just 1 mole of pentane being burnt, we don't have to do anything because 1 mole of pentane has at least 3,509 kilojoules. So that's nice and easy. So times, so remember unrounded value in the calculator, 3509, and I get -6090, 3 sig fig kilojoules. All right, then we're just going to do the same thing for hexane. All right, moles of hexane is equal to 125 grams of fuel. So we're going to have less moles of it because it is a larger hydrocarbon. Right. But you'll also see that it's got a much larger delta RH value. So -4158 times 1.45, but we're using the whole unrounded value in our calculator, is -6040 kilojoules. So it's pretty close, right? But we haven't answered which fuel, we haven't asked the question yet. Okay, so it's which will produce more heat energy. So I'm going to say pentane produces 50 kilojoules more heat energy than hexane. Cool. So just a really nice, clear answer that actually answers the question. All right, I hope you enjoyed my video. I hope I never have to use this channel again. All the best. Remember, there's more practices in your exam booklets on slide 17, so go ahead and do those now. And if you've got any questions, pop them in that document that's linked into your go-to document. All right, I will see you next week. Bye.